Today in this video we're going to explore how proofs are different from normal math classes, and we're going to look at a few examples. So for proofs help us to think deeper into the knowns and the unknowns of the mathematical world. It forces you to actually understand what's going on in each problem, and it's different from other math classes because you are focused to think deeper into elementary ideas and to prove why they are right, not just to accept them as true. For example, we'll look at this example. You have A intersect B is contained in A union B. Although this might seem very elementary, it forces us to delve deeper into the main details of why this statement is true, providing you an actual understanding of the mathematics behind this. For this proof, we're going to use the definition of lim sup an and develop a reasonable definition of lim inf an for a bounded sequence of real numbers an where n is equal to 1 and goes to infinity. By defining a sequence Zn for each n within the natural number system, we need to prove that this sequence converges. We will then develop a bounded sequence of real numbers an where n is equal to 1 and goes to infinity, where the sequence Zn where n is equal to 1 and goes to infinity does not converge to the inf of an. One of the most important things in proof writing is how you organize your thoughts. One of the main things you want to do is start with an if-then statement. This consists of your know and your show, and your know and your show essentially is what you know to be true and what you're trying to prove is true. So for example, in this proof, our if-then statement would be if Zn is the infimum of the sequence AK where k is greater than n for all n within big N, where the sequence an is a bounded sequence of real numbers, then the sequence Zn converges. From this statement, our know is that Zn is the infimum of the sequence AK where k is greater than n for all n within the big N, where the sequence an is a bounded sequence of real numbers. Or this is the first part of the proof. It is the if portion of the statement. Our show comes from the then part of the statement, so anything following the then part of the statement. So our show is the sequence of Zn converges, so this is what you need to prove. The next thing you want to do in your proof is to expand your know. So what you're doing when you're expanding your know is you're trying to find any definitions that might be helpful for you. And when you get these definitions, you want to make sure that they have things you can work with, such as variables or expressions that you can manipulate with your hands. So the first main definition we're going to need to know is the definition of sup. So that states for every epsilon greater than 0, there exists an element x within Zn such that s minus epsilon is less than x, and then s is equal to the sup of the set Zn. And, two more definitions we're going to need to know is the definition of lim sup, which is of an. So you're going to let an be a bounded sequence of real numbers. So an is equal to a1, a2, a3, all the way out to an, and it's bounded. So the lim sup of an is the limit of the sup of the sequence of ak, where k is greater than or equal to n. So what that's saying is that the limit of this sequence is where k is greater than or equal to n. We also need to know the definition of lim inf of Zn, which is we're going to let Zn be a bounded sequence of real numbers. So Zn is again Z1, Z2, Z3, and it's also bounded. So the lim inf of an is going to be the subsequence of an, which is zk, and we're going to take the limit as it approaches infinity of zk. So you're going to need to have Z1, Z2, Z3, Z4, and then you're going to take the limit of each one of those of that sequence, that subsequence of an, and that will give you your lim inf of the sequence an. The next thing you're going to do is expand your show. So what do you need to prove what you're trying to prove? So there's any definitions you might need. So the main definition we're going to need is the definition of convergence. And the definition of convergence says that the absolute value of xn minus x is less than or equal to epsilon. So that says for every epsilon greater than 0, there is a capital N within the natural number system such that Zn minus L, which the L should be your limit, which is less than or equal to epsilon, wherever little n is greater than big N. And in this case, for this proof, your limit is going to be the sup of the set. Again, you're going to want to expand your show to include any theorems that are necessary for your proof. The more you have written down here, the easier the proof will be. The last portion of the proof is to test your problem by using an example that satisfies the hypothesis and one that doesn't satisfy the hypothesis. So this will show you why any of the theorems are valid or any of the things that you used are valid within your proof. So we will explore this example in a little while. So here at the top of the page is the know and show again. It also has the expanded versions of the know and show and the definition of the conversions. So the first thing that we need to do in these proofs is see what we're looking for. So we're looking for n, capital N to be specific. So the first thing that you need to do is let epsilon greater than 0 be arbitrarily given. That's the first thing that happens in any one of these proofs. Next thing that you need to do is state that there exists an x within the sequence Zn such that the sup minus epsilon is less than x, which is less than or equal to s. That basically is saying that you have your sup and you're subtracting any epsilon's given, and you're going to be able to find a sequence member within those two that's being squished between the sup and then the sup minus your epsilon. To go a little bit further, x is in the set Zn, which also looks like x is Zm, so that's for any m within the natural numbers. So that means that the Zm is any term within Zm where m is equal to a natural number. So this sequence actually is increasing, this subsequence, and that's given by this portion right here. So the sequence Zn is increasing because if you have the inf of the sequence, which would be Z1, Z2, all the way out to Zn, the inf of that sequence, so this will be equal to Z1, Y1. So the inf of that sequence is either going to be Z1, it's going to be a limit, or it's going to be another portion of that sequence. So you can say that Y1 is less than or equal to Y2, and you could say that because Y2 will be equal to the inf of the set starting at Z2, because when you come to the next set, you're going to drop your first term. So you're going to come out to Z2, and you'll go Z3, Z4, all the way out to Zn. And then the same thing is true for this set. So the inf of this set right here is either going to be Z2, or it's going to be a limit of the set, or it's going to be another element within the set. So the Z2 is going to have to be greater than Z1, greater than or equal to Z1 based on the set, because the inf of this set is being taken out. So you're coming up to this set, and then you have the same inf or you have a new inf. So it's either going to be greater than or equal to Y1, and the same is true for Y3, Y4, Y5, and Y6. So now that we know that our set is increasing, we can let capital N equal m so that Zm is less than Zn for all elements corresponding to n that are greater than m. So because the set is increasing, if n is greater than m, then the element corresponding to n, which would be Zn, must be greater than Zm, which is the element that's corresponding to the m. Since S is the sup, that also needs to be greater than or equal to the larger portion of the sequence. So Zm is less than Zn, which is less than or equal to S. So because the sup must be the greater than all the elements within the set, because by definition of the sup, it is the greatest upper bound of the set. Because the sup is the greatest upper bound of the set, we can say that Zn minus S is less than 0, which is less than epsilon, because if you subtract the sup from any member of the set, you will get a negative number, because the sup is the greatest upper bound of the set. And then epsilon is greater than 0 is always a given. So that can be said that Zn is less than Zn minus S is less than 0, which is less than epsilon. So now we can say that by definition of convergence, that the absolute value of Zn minus S, which is our sup, is less than epsilon. So at this point, we're proving that this sequence that we have, Zn, is actually converging. So we have S minus epsilon is less than Zm, which is less than or equal to Zn, which are both portions of the set. So they're both numbers within the sequence of the set. So they're less than the sup. They're less than or equal to the sup for all little n greater than or equal to m, which is also m, if you remember from before, is equal to big N. So from this, what we're saying is that you could take the sup and you're going to have elements within that sequence that come between the sup and the sup minus epsilon, which is just a small portion of the set. So that's kind of the definition of the sup. So it's kind of squishing those two between the sup and the sup minus epsilon, which is showing the definition of convergence in this portion of the proof. So if you do a little bit of math out here, you're subtracting S to the other side, and you're focusing on this portion right here of the inequality. So you subtract S to the other side, you're going to be left with negative epsilon is less than Zm minus S. And then if you multiply by -1, you get epsilon is greater than S minus Zm, which is the definition of convergence. So you have just proven that the sequence Zn converges. A good helpful tool that you'll have is a proof writing checklist. So this proof writing checklist is a great tool because you can go back after you've written your proof to make sure that you've done everything, to make sure that everything is spelled out clearly. So the first check is my proof defines all variables used. So you can go through your proof and make sure that you have all your variables defined. Make sure that any definitions are also defined. So you should say, and your proof should also use words to explain any algebraic functions. So anytime you're manipulating an equation, you need to make sure that you're explaining what's going on, because sometimes it's not always very visible as to what's going on. The next portion is my proof states clearly where I'm using the hypothesis, so the no. So you want to make sure that you're saying by definition of the sup or by definition of convergence. You want to make sure that you're referring back to those definitions so that people aren't left out in the cold. And then the next portion is that my proof states what method or approach I'm trying to use. So you want to show, like, if you're going to prove the proof directly, by contradiction, by cases. So this gives you, your reader, an idea of how the proof is going to be set up. And the last portion is I cite all definitions and theorems correctly and rely on mathematical formulas. So you want to go back and make sure that your definitions are correct and that any of the mathematical functions you did are correct, so that your proof in turn is sound. So here we have an example of a bounded sequence of real numbers that does not converge to the sup. So we're looking at specifically this sequence, n minus 1 over n, where n is 1 and it goes to infinity. And we're going to focus on the subsequence Zn. So the sequence starts out 0, 1/2, 2/3, 3/4, and it continues all the way on. So our Z1 would be the inf of the sequence 0, 1/2, 2/3, 3/4, and so on. So the inf of that sequence would be 0. Your Z2 would be the inf of the sequence 1/2, 2/3, 3/4, because you're going to be dropping off that first term in your sequence. So your infimum is 1/2. And if you were to continue to Z3, you'd have the inf of 2/3, 3/4, 4/5, 5/6, and that infimum would be 2/3. So at this point, you have a sequence whose the limit of the infimum is increasing. It's also a bounded sequence, but it is not converging to the sup.